am Anuradha Mathur. I teach physics at Modern School Vasant Vihar, New Delhi. We have talked about magnets and their basic properties, talked about a magnetic dipole and calculated its magnetic field. Today we are going to learn about what happens to a magnetic dipole when it is in the field of another magnet. That means, we will need to qualify what kind of a magnetic field is there around the dipole. It could be a uniform field or it could be a non-uniform field. What would generate a uniform field? If it is a dipole, you should never be expecting a uniform field. However, if the magnet is very small and it is placed in the field of another magnet and the second magnet is large enough, then you can say that the small magnet is placed in a uniform magnetic field. Much like we are in the uniform magnetic field of the earth, say for whole of Delhi. So, it is very large space, but because the earth's magnet is very large, it can be said to be so. However, if you are working in a lab and your magnet is large, then it would not be creating a uniform magnetic field. Now, we are going to see what will happen to a small magnetic dipole, like in the case of a compass needle, when a magnet is brought close to it. Let us see, here is the magnet and here is the compass needle. The needle is the small dipole which is free to move. Now, the reason that it is moving or deflecting is because a force of attraction is acting at one end and a force of repulsion at the other end. Because the needle is small, this is almost same value. So, the two sided forces here are going to be acting on this dipole in this way. If they are both equal, they will create a torque, and that is the reason why this is going to rotate. We can use this idea to calculate the value of magnetic strength of this magnet. You can calculate the moment of inertia of a magnet. You can do many things with it. However, let us first study what calculations we need in order to talk about the torque which is created on this, how much is the torque, what is the energy stored in it, if any at all. And I think you can guess from your knowledge of your electric dipole in a uniform electric field that the dipole is going to store some energy if it is so. Likewise, this is also going to store energy. Why? Because if I let go of this magnet, this is going to be set into oscillation. It will oscillate till its energy is lost and will come steadily back in its north-south direction. Let us now calculate the torque acting on this needle, which has say a moment of inertia of I, and it has a magnetic moment of M, and it is placed in a magnetic field of strength B, provided by obviously some external magnet. So, what will be its value? It will be m b sin theta. What is theta? Theta is the angle between magnetic moment m and B, B the external field and the magnetic moment of this particular needle. In equilibrium, this torque should be equal to I, the moment of inertia, into the angular acceleration that it is creating, minus m b sin theta. Equilibrium, why? Because at the moment it is not moving anymore, and therefore, you can equate the value of torque that is there with the restoring force which may be there inside this needle. So, it becomes this value alpha from here is going to be given by omega square theta from our previous knowledge of simple harmonic motion and the oscillator, and we talked about the acceleration in the setup to be omega square x. So, here the displacement is angular, so it would be theta. So, this expression will therefore give you that the reason why this oscillates is going to be because of this torque, and once that is removed, this stored energy is causing it to move further. Now, the value for torque will be magnetic moment multiplied by B, the intensity, sin theta. Theta is the angle between these two, okay, between M and B. In equilibrium, however, this torque should be equal to the internal restoring force that may be set up, because otherwise the needle should rotate, but it does not, it stops after some time. So, the reason for that is that the internal restoring force which is set up must be exactly equal to this. So, in terms of moment of inertia and the angular acceleration which it is creating is equal to minus m b sin theta, which is I omega square theta. Omega square theta, if you remember from your lessons on simple harmonic oscillator, you calculated this as the value for acceleration for the oscillator in terms of omega square x, and here x is angular displacement. So, it would be omega square theta. Now, if theta is small, then and also in radians, you can then say sin theta is equal to theta, and for that oscillator in terms of omega, the periodic time t would be given as 2 pi I upon m b. Now, this gives you immense possibilities. You can find the frequency of this oscillating dipole, you can find the time period, you can find the moment of inertia, or if you know the moment of inertia, you can find the field B of the external magnet, you can find the value for pole this magnetic dipole moment for it. This therefore, is a very important result and can be used for multiple things. What is the energy stored in the dipole when it has deflected from its mean position? If you were to calculate that, then it would be just energy is work done. What work would be done? Torque multiplied by the angular displacement. So, U is torque into angular displacement, which in turn can be integrated for all the values of theta. So, that will be U is equal to integral T d theta, integral m b sin theta where you have substituted its value, and minus m b cos theta. So, this energy is a dot product of two vectors, m the magnetic moment and b the magnetic field, which is the external magnetic field. Do not forget, we are talking only of uniform magnetic field. So, what will be the minimum potential energy? When would that be? When would this dipole be most stable in an external field? Obviously speaking, when the theta, the angle between m and b is equal to 0. When it is 180, it is going to be the most unstable condition. That means, the dipole would tend to deflect right back and turn completely in order to restore its position. So, it will rotate 180 degrees in order to become stable. See like this? Full deflection of 180 degrees is going to be viewed, because you will understand that the two poles that will come opposite each other will have to be opposite, and the ones that is going to be at the farthest end would be the same polarity as this one. So, for stable equilibrium, this is most essential. Does it happen in nature? Is it taking place anywhere? Is it worth anything? Why are we considering it so much? Do you know, birds, bacteria, insects, they all can sense this, and the dipole associated with the electric currents formed on account of the electrons in the atoms that form them make them sensitive enough, and therefore, you have flight of birds for say migrating birds, certain bacteria down below on the seabed react to this dipole ability and change their positions accordingly to have the minimum potential energy. That means, they can stay stably and remain at, I should say, at peace with themselves in their surrounding. So, our setup is that we have a small dipole which is resting in the north south direction, a scale attached to it from where we can take some measurements, and we want to compare the strength of two magnets. So, I have one magnet here and I have another one which is different, and I want to check out which one is stronger. So, supposing I bring this here and a certain deflection occurs because of the magnet which is placed, and I try and see what will be the influence of the other magnet when I bring it close. Oh, it is in the same polarity. Let us see, it cancels the effect, but at a distance which is further away from the first one. That means the one in my right hand, that is the red magnet, is stronger than the black magnet. You can compare it, you can take measurements, you can find the actual value of its strength. If you can calculate for any one of them, you can find for this different shaped one which is not a bar magnet, but just a commercially used magnet for a toy or maybe in any other system. So, it allows you a lot of possibilities, and of course, the intention being how strong is this magnet, what is it going to do for you, etc. So, today you have learned about a dipole in a magnetic field. We have qualified how to get a uniform magnetic field, and you have been able to calculate that the dipole will get a torque acting on it. You can then calculate how much energy can be stored in it. If it is allowed to vibrate, you can even calculate the moment of inertia of the subject magnet, or you can even find out strengths of different magnets. You can use the idea as in a magnetometer, which we tried in the last experiment, that you can compare the strength of magnets. So, with immense possibilities with the dipole and its study in magnetic field, you can have a lot to do with it. You can try some numericals by actually putting values of theta and calculate the amount of energy involved in it.